All right, this is the Six Shapes of Algebra continued. We were talking about lines. We were talking about what I call half parabolas, which is, like I said, cubes aren't really half parabolas, but they're so close. I'm okay with it. All right, okay with that little saying. But circles are the next lesson. All right, so and we should know, and we already do know, I suppose, we've already covered this equation of a circle. Now, if I remove the h and the k, I wouldn't need the parentheses any longer. And so this equation would be x squared plus y squared equals r squared. Right? If I remove the h and remove the k, I'd have x squared, but I don't need the parentheses around it. All right. So I call that the basic circle. The basic circle is x squared plus y squared equals something. In this case, 4. So we had several sections on translating graphs. I'm trying to get this to work for me. Okay. So I'm going to pick up that circle and move it. Now, originally the circle was x squared plus y squared equals 4. And what I mean by that is it was centered at 0, 0. So h was 0, k was 0, like it wasn't there. And that's our basic graph. But if I move that graph here, almost all students will get this. Not from fluency, but because of the way the circles are packaged or presented to us, they can just match it up to this equation. And the new equation is, let's see if I can get to it all fit, x minus 3 squared plus y minus 2 squared equals 4. All I did was introduce this h and this k, and I have this new equation. Circles are there to teach us what subtracting 3 from x does, not just to the circle, but to any graph. So a lot of times when somebody will ask me, how do I want to do this? Okay, let me draw a half parabola right here. And let's say this is a clean half parabola, meaning it really does go through this point, which is 1, 2, 3, 4, and then 2 away from it. Cube root would go a lot farther. All right. What's the equation of that graph? Again, tough question if you're not quite confident with it. Well, the original graph was a half parabola here in quadrant 1, which is y equals the square root of x. So if I did this h and k, literally I'd get y minus 2 equals the square root of x minus 3. If I just listen to the circle, that's the equation I'd get. It's not the answer to any question because we don't write functions with y minus 2 in them, right? I'm obligated to take that 2, to add 2 to both sides, let's say, to cancel this. And so I'm going to get y equals the square root of x minus 3 plus 2. So a lot of times when the student has a problem with this graph, like how do I graph this? I like to say, ask the circle. Because the circle has a lesson. And what's the lesson? It tells us how horizontal shifts are created by x minus h. And by extension, y minus k is a vertical shift. It gives us a new or old, I don't know, more familiar perspective on translating any graph. All right. I'm not going to do it here because I'm just talking about shapes, but it seems to be the easiest instance of completing the square. Completing the square is something that happens 3 or 4 different times in an algebra class, but students seem to, respect the fact that they have to complete the square for a circle, and they have a little trouble completing the square some other times, it seems. But I just thought I'd throw that in there on my outline, but won't do that. I think we got it. Yeah, circles tell us how things go. And I'm operating under this assumption that you might not be operating under because you don't see it. But, let's say I asked on a final in Algebra 1, or let's say Algebra 2, someone to graph, the class to graph this. I would say 90% plus get it right. Then I ask them to graph this, and I'd say we're down to about 50% getting it right. And the reason is not terribly clear, but in my mind, the reason is circles are always shifted. Students are ready to do the H and K thinking with a circle, but they're not willing to ask the circle, what's this? If you just reverse the steps, you don't have to do that either, but if you said, well, this could be a -2 on the y, so I know that h is 3, k is 2, hk, there's my, however you might do this. But, if you know how to do one, you should know how to do the other if you've reached this fluency where you're making these connections. If you're not, this is just a flashcard moment that you practiced, and this is a flashcard moment that you didn't practice. And we get that huge discrepancy in the number of students who get one, but not the other. All right. Hopefully that's none of us, right? Because we've seen it. All right. So when I said there are 6 shapes in algebra, there are really 6 lessons in algebra. There aren't 6 shapes because ellipse and circle are really the same shape. Circle is just a special case of the ellipse. But since there are 6 lessons, I go ahead and give it another shape. And actually, we do treat ellipses a little differently than circles in the book as well. But I have this thing here, this circle. It is a circle. It's also an ellipse, technically speaking, it's both. And it's the equation x squared plus y squared equals 1. And we know why. It's x squared plus y squared gives us a circle centered at 0, 0, and 1 is the radius. All right. So this is the way ellipses are, I say normally written, I should say always written. But for our purposes, because I want to learn what the ellipse is here to teach us, I went ahead and divided x directly by a, then squared it. I mean, they're equal. And divided y by b and squared it, they're equal. All right. So what's the lesson? The lesson is the parabola, ellipse. So that's a typo. The ellipse tells us that x over a is a stretch a units along the x-axis. Y over b is a stretch b units along the y-axis. So this idea of stretching a graph, let me do that. I'll tug this graph 3 along the x-axis and 2 along the y-axis. So I still have the original graph here, but what graph did I just create? Well, I created, let's do this in blue to indicate it's the blue graph. I created, well, I stretched it. So how do you stretch? Along the x-axis. You divide by 3. So from x squared to x over 3 squared. I'm copying the plus sign I had before. And along the y-axis, I stretched it 2. So this equation is that new graph. And how did I get it? By memorizing the ellipse or by learning the message the ellipse is trying to teach me. And the message the ellipse is trying to teach me is, I'm a stretched circle. That's what ellipses are. They're stretched circles, and I'm assuming they're stretched. They could be compressed if I divided by a fraction, but they're stretched circles, and very predictably, it's very predictable how they're stretched. Now, there's one thing I'm doing here very aggressively, and that is I'm making the stretch visible. A more common way of seeing or being presented a question would be something like this. You can't really tell what I'm dividing x by. I'm dividing x squared by 9, so I'm very aggressively making it visible, but I know that if I do that, divide by x by 3, I stretch it 3. At least that's what this graph is telling us. So most students take this, and graph this without ever thinking about the circle, but stretches are a thing. In fact, we've covered them. So what's the difference between y equals x square root of x versus y equals square root of x over 2. All right. So put in some points here. All right. Well, I want to stretch this graph along the x-axis. Let me leave myself much room for that. All right. So this is a message to stretch this along the x-axis. So here, x was 1. I want x to be 2. I want to be twice the size. Here, x was 4. By the time it reached this height, I want it to be 8. So to stretch that graph along the x-axis, it would look like this. I don't know. I could have gotten this numerically just by plugging in points. For example, if I put in 8, I have 8 over 2. And 8 over 2 is 4, square root of 4, and I could calculate that. Sure. But if you want to learn the lesson the ellipse is trying to teach us, learn that this is a stretch along the x-axis. Now, a stretch along the y-axis is usually hidden even more in most functions, because in a function, you're just never going to be handed y over a number. So I said y over 3 equals what function? Well, let's do square root of x again. I know what this is. It's a graph stretched along the y-axis, but it's a hidden operation, because it's never handed to you this way. How is it given to you? Y is always all by itself. And you have 3 square root of x. So that would be this blue graph stretched. It's 3 times higher than it was before, because it's a stretch along the y-axis. I'm not saying you couldn't know that lesson without learning it from the ellipse, but hey, if the ellipse teaches you that lesson, use that. That's part of fluid and fluent thinking. I also have this. A times x by extension is a compression along the x-axis. So, in other words, I know these are getting kind of crowded. if I had said 4x squared plus y squared equals 1, what is that graph? Well, it would be compressed along the x-axis, just that fast. Now, how would you do this in slow speed, in slow motion? Well, in slow motion, the book would tell you to think of this as x squared, 16x squared, plus y squared equals 1. And then we think of that as x squared over 1/16. And this is a good example of what I mean by the slow way of thinking is really numbery. Why am I doing this whole x squared over 1/16 when it was 16x squared? Well, mathematically that's equivalent, but I'm doing it because a lot of times students are, we overemphasize, put it in this form, put it in standard form. We need the 1, we need the y squared, we need the a, x over something squared. So this identifies a squared is 1 over 16. So a is, I was off the page for a second, 1 over 4. So in other words, yeah, we can get there, but if you learn the lesson that you were meant to learn, you're already there before you draw anything. That's one of the things I say, that fluency is immediate, fluency is quick, fluency is understanding the joke without having to be explained, without needing an explanation. And that's what the ellipse is trying to teach us. So the one thing I would just want to emphasize before I move on here is, yeah, if you talk to another teacher, the other teacher might say, no, circle and ellipse aren't different shapes. A circle is an ellipse that, before it's been stretched, but it still qualifies as an ellipse. But they're very different lessons. So that's why I wanted to talk about that. There's 2 more to go. So only been 4. Hyperbolas. So one of the 2 equations for hyperbolas. Now, hyperbolas, the lesson's pretty obvious with hyperbola. I don't think anybody's surprised about what I'm about to talk about. But let me put in. So I put in this box.
Time to plan dinner.
And the box goes 2 on the x-axis and 3 on the y-axis. So what graph are we talking about? We're talking about x squared over 2 squared minus because it's a hyperbola, y squared over 3 squared equals 1. So if you're given x squared over 4 minus y squared over 9 equals 1, you will immediately kind of just draw this box. And the box, because 4 is 2 squared, 2 along the x-axis. All right. Now, I'm not sure how well I'll do this by hand here, but I want to draw in a different color. A hyperbola that does what a hyperbola is supposed to do. I feel like I nailed that one. All right. That does what a hyperbola is supposed to do. What is it supposed to do? Well, it has a certain shape to it, but there are a couple of things. A couple of lessons. A hand-drawn graph just is not complete without the asymptotes pictured. If I didn't, I'll take away the asymptotes and I'll show you why I don't particularly like that graph in a second. Never turn away from an asymptote. So if I had drawn that one incorrectly, I might have gone like this, where I kind of completely ignored the asymptotes. Students do an awful lot with hand-drawn graphs of hyperbolas. You should be getting closer and closer to the asymptote, because asymptotes tell us how the graph leaves the box. Asymptotes are forever. Asymptotes are what happens outside the box. I should also go along this way. And by the way, there's a reason why I'm not going along the y-axis and drawing the one down here. We call it the transverse axis. If you start with the letter X, this is a new lesson, you draw it on the x-axis, crossing the x-axis. If this had been switched, where I had y squared over 9 dot dot dot, minus dot dot dot, still y squared over 9, same box, but I would have oriented the graph differently if you switch the one you're subtracting with the other one. But that's not the specific thing about this lesson. What are the lessons? Asymptotes. If I were to get rid of the asymptotes, I don't know if I can because of all the and the box and the letters. All right. Didn't mean to get rid of the x and y axis, but that too. All right. If I get rid of all the supporting stuff, it's still a hyperbola. In fact, it's definitely a hyperbola, but it loses a lot of what we would understand on this graph. Without the stuff that I got rid of, it's just not, the picture is just not complete, especially to a human looking at it. So the box was nice to have, the lines are nice to have. The graph itself is the star, and that's in fact why I drew the asymptotes as dashed lines and have students do that in my regular classes. Draw them as dashed lines because anything solid should be the graph itself. The dashed lines are just there to help. But it's one of the times when we learn to draw asymptotes and we really kind of emphasize them. And we've emphasized asymptotes for other graphs, but not just that. All right. What does this graph, exponential and logarithmic graph? All right. So the exponential graph is this graph right here. It's y equals a to the x, like let's say y equals 2 to the x. And we know that if you put in 0, you get 1, because 2 to the 0 is 1. Doesn't matter whether it's 2 or some other number, but all right. And if I put in 1, I'm going to get 2, so it's twice as high. If I put in 2, I'm going to get 4. And anyhow, there's this graph that just keeps on doubling. If it's 2, gets twice, the points get twice as high if I step over one dot. Move over one dot, it's twice as high as it was before. Move over one, it's twice as high again as it was before. So that's exponential growth. But what is it here to teach us? Well, when you switch the x and the y, you're creating the inverse function. And inverse functions are reflected on this line y equals x. And I think that's probably the most important lesson here, and that is this, if I do switch them around, I get this. What is that? Well, that is y equals log base 2 of x. It's the inverse of this function. And I know it's the inverse because I can see it in the picture itself. Anytime you have a function and its inverse, well, on the same graph, or anytime you have two functions on the same graph and they're reflected in this line y equals x, then you have inverse functions. Now, one thing, I usually can't do this, but since I'm using a tablet, I can kind of tip this thing over. Sometimes students, when I put orient the line y equals x like this, they see the symmetry a little bit better. But inverse functions, that's really what logarithm teaches us. A little harder to see here, but this is when a is a fraction, like 1/2, a number less than 1. Oh, I think I got these backwards. I worked so hard on getting those straight somehow. Got it earlier. A is greater than 1. Man. So my example is good, 2. And this would be if a is between 0 and 1. All right. I recognize it because it's a decreasing graph. A decreasing graph suggests a is less than 1. It can't be less than 0, though, so I'll write it that way. All right. Now I had this error on here, and I fixed it, but not on this version somehow. All right. Where those were switched around. All right. If that's the graph, what happens if I switch it around? I get this. It's a little hard to see, but maybe you can see how those are reflected in that line y equals x. This would be y equals log base 1/2 of x. Because they are inverses, they have that relationship that inverse functions have. All right, so I'm going to end this whole thing on a riddle. Not a joke. I've been saying fluency means you understand jokes, but a riddle, all right? So the riddle is, if I had the letter B, we'll come back to this one here. Now, let's get that off the page. If the letter B, it behaved like a function. If this behaved like a function, what would minus B look like? What would minus B look like? What would minus B look like? All right, I'm going all the way back to the first video on this, but I'm saying if it behaved like a function, meaning it changed its, not shape, but it changed shape the same way square root of x changed shape. Do you remember? If I had something in quadrant 1, this would kick it into, this would reflect it across the y-axis, right? And I'd get this. If you're getting this joke here. It's not a joke. All right. Square root of x. The square root of minus x would be if I flipped it. So if I put a b here and I flipped it, I'd get d. All right. That's what a minus there do. All right. It takes the graph and brings it down here, right? So I would get, what happens if I take the letter B and flip it? I get the letter P. If B behaved like, the letter B behaved like a function, right? What would minus B be? All right, I know what you want to do. You just want to cancel, but not, if it's a function, we're not allowed to do that. All right, let's assume we're not allowed to just cancel that and get B. I'm talking about if it behaved like minus x. What letter am I talking about here? Well, Q, except I shouldn't put the little tail on it, right? It's Q. I have one more part of this riddle here. If the letter B behaved like a function, what would B inverse look like? And now, in an algebra class, this is, I keep on saying if it behaved like a function. In an algebra class, the letter B behaves like a number. It would be 1 over B. That's not what I'm talking about. I'm saying if this behaved like a function, what does the inverse of a function do? According to logarithm, exponential and logarithms, right? It takes the graph and flips it like a pancake, but I flip it through this line y equals x. So I even drew it here. Well, we get this very non-letter. In fact, I racked my brain trying to figure out are there any two symbols that, okay, we get this very non-symbol, right? So if I just flip that. All right, now I was trying to figure out, well, what letter would this work for? And I think I came up with one. If I were to take the letter H and flip it, I'd get a 2 with a long stem on it. That's the best I could find. If I were to reflect H in this line, now if I reflect H over here, it would just be a non-existent letter. But I just wanted to go over that. If I were to, I'll put parentheses around there. If I were to call this my original function and say, all right, here's what I want to do. I want you to reflect it like an inverse function. You get that shape. This is a lesson that, this part of the lesson, I almost thought of not putting in here. I mean, I do it in my face-to-face classes. I almost thought of not putting it in here because I feel like it might cause more questions than it helps. But I think it's important for you to understand that life is shapes. You've been doing this thing about shapes, and I'll admit it took me a while to find this one. I mean, I forget it, and I say, what was that? What was that combination that I could reflect and it means something, right? There are letters that are really easy to reflect, and there are actually questions like this in some math classes where they have students reflect letters just to learn about, but more in a geometry class, right? So they're not really integrating all of this. But questions like these, I like them. I think they're good for a certain type of understanding. But I'll put it this way. They don't really put points on your test. What puts points on your test is the flashcard moments, the facts, the calculations, the homework. Some people would call it the heavy lifting. Math becomes very interesting once you reach fluency. Any subject does. Becomes more interesting once you reach fluency. And chapter 7 is really our first chance to really knock on that door and hopefully have a chance to understand what it means to be fluent in a subject. All right. Now, after all of this, you're still going to put points in your test by doing the homework. In other words, not much has changed in your life as far as moving forward on most of the problems here. But at least you understand why the problems are here. And maybe you've made some connections that you wouldn't otherwise have made. So there really is a reason why we have these questions, we do these things, and it's because it's trying to give you a chance of making connections and being fluent in the subject of shapes and learning all the lessons from there. All right. Well, like I said, this was a 2-part video, so this is part 2 of that video. Hopefully you agree with me that maybe not the most important lesson of the course, but somewhere near that. Some of you already noticed I'm placing this video in places I don't normally place my videos, or I should say in addition to where I place my videos. I place my videos in playlists and in the lessons, but I'm going to blast this a few other places. And I'm doing that because I just want students to bump into it a little bit more than some of my others, because in my opinion, it's the most important lesson of the course. With that, that is my overview of Chapter 7. We're still going to have Chapter 7 individual videos where we study the flashcard moments because we have to. But hopefully this gave you some perspective. And with that,